Hi, welcome to your lesson on inverse functions, part two. All right, there are some more challenging concepts that came up probably in the practice or just in our discussion. So let's get on with it. First of all, let's recap a couple main points. Here's a function, f of x, and it has an inverse. And inverse, we use this notation, f with that little -1 there. It looks like an exponent, but it is not. There's ways to turn this into that, and hopefully you've practiced those techniques. There's another function, g of x, so its inverse would be called g with the little -1 there. So g inverse of g is this. Again, there's a way to turn that into that. Okay, we also learned that inverses are reflections across the line y equals x. This is the line y equals x. Here's some function, and notice when you invert it every point, you just interchange or exchange the x and y values. Here's -2, 0. So a corresponding point is going to be 0, -2. Or we have 2, 4. So a corresponding point on the inverse will be 4, 2. And finally 3, 7 will become 7, -3. And then if you plot those points, you will notice it's always a reflection like that. So here's two inverse functions as well. There's y equals x, and you can see they're mirror images of each other across that line. And then we have this parabola, x squared. Here's y equals x, and notice when you reflect that parabola, it ends up being right here. There's even this portion here that they go on opposite sides of the mirror. We also learned that some functions, because this is a function, creates an inverse relation that is not a function. So this red one, the inverse, is not a function, because if you did the vertical line test, it would pass through and hit 2 points. All right, here's another example. Here's one of these inverses that goes across, back and forward across that y equals x line, but the inverse is still a mirror image like that. All right, so now let's take some notes. We're going to move on to some tougher ideas and concepts and tougher algebra, basically, for inverse functions. So here is a rule you should know. If you have a function, f of x, and its inverse, the inverse of f of x, then the composition of the two will always equal x. You may have noticed this in some of the practice problems. What this means basically is if you take the inverse function, which is in blue here, and you put it inside the original function, then you will get x every time. Or likewise, if you do the opposite, if you put the original function into the inverse function, like this, you will get x as well. So let's take a look at some examples that show that. Here's one that we already found the inverse of in the previous lesson or video. We have this function. There's the original function. To find an inverse, we usually will write the f of x as y first, just to make it a little easier to see. Then by the definition of an inverse, we create the inverse by exchanging or interchanging the x and y values. So that becomes x, this becomes y. So here we have the new function. This is now the inverse function. However, this form is not easy to work with. We want to solve it for y, so we have the inverse solved for y. So here's the inverse. Now we're going to move things around. The first I added 1 over here. Now I see this half, so I'm going to multiply everything by 2 to cancel away that half. This became 2x plus 2 equals y. So I've solved it for y. So now you can rewrite it in inverse notation. So instead of y, I wrote the inverse of f there, and then there's that function we found. So here's the original, here's the process, here's its inverse. So now we're going to look at that new rule we learned, that if you put the inverse into the original function, or you compose the two, you will get x. So let's try that. What does that mean? So here again, this means the inverse is going into the original function. So here's our original function, and I'm replacing this x with the inverse, right? So that is being replaced with the inverse, and that means this x is being replaced with the inverse. So I took the original function, there it is, half x minus 1, but the x has been replaced with the inverse function, which is 2x plus 2, right there. Now this, let's see what it simplifies to. Half multiplied through here is going to make half of 2 and half of 2, so basically it's going to become x plus 1 equal minus 1, and 1 minus 1 is x. So as we can see, when the inverse was put into the original, inverse put into the original here, we ended up with x. Let's try the opposite of that, the original put into the inverse. So now we're going to begin with the inverse function, and we're going to take this original one and put it into this one. So here's what happens. So again, here's the inverse, 2x plus 2, so this is 2x plus 2, but the x has been replaced with the original function. which is half x minus 1. So that goes in there. Now we can multiply this by 2. 2 times a half is 1. 2 times negative 1 is negative 2. And we have plus 2. Notice those again cancel, and we're left with just x. So the rule holds. When you put the inverse into the original, we get x. When you put the original into the inverse, we get x. All right, let's look at some harder ones like this. So why does this work, you might be wondering? Why, when we put the original into the inverse, do we get x? Let's take a look at an example using some coordinates. So here's an original function. Here's its inverse. Don't worry about how that went to there right now. Just let's look at what happens. We're going to put an x value of negative 2 into the original function. So negative 2 goes in there. Work it out, and you get a y value of negative 3. So now that is a y value of the original function. So now that y value of the original is going to be put in as an x value into the inverse. So that y value again turned into the x value here and is substituted into the inverse here for x. So basically that means the same thing as here. We took the y of the original function, which is this, f of x is the y of the original function, is put into the inverse function as its x value, right? Because this normally would say f negative 1 of x. So this thing replaces the x value here in the inverse. So again, the y becomes the x value in the inverse one, and then you solve it and you end up getting this value. And this value, y equals negative 2, is the x value of the original. So again, when the y of the original goes into the inverse, it pumps out the x of the original. So that's kind of behind the scenes for that. All right, let's look at a tougher example. Whenever you have fractions with x on top and bottom, finding the inverse is a little more tricky. It takes more algebra to do it. So first of all, we're going to rewrite that as y equals instead of f of x. Now we're going to write the inverse of that. Again, by definition, the inverse occurs when we interchange the y and x, so that y becomes x, and both those x's become y right here. Now we're going to solve this for y, so we're going to solve for y. This is already the inverse, but we want to rearrange it so we have y equals in that form. So how do we do this? Well, we can multiply both sides by y first. So we'll get xy over here, and this y from the fraction is gone, because if you multiply it, it would cancel. Now you want to get the y's on one side together. So here's that y already. Here's 2y, so I'm going to move that over to that side. So I added 2y. Now I can factor a y out of here. There it is. Once I factor that, I have x plus 2 here, which now you can divide both sides by x plus 2. So you end up with solving for y like that. This has been taken from this side by dividing both sides by that. So here's your inverse. And we can write that using inverse notation. All right, so that's a little tougher because it had variable top and bottom here. All right, so now that we have that, here's the original. This is the one we just did. So this is the original, and here's the inverse. So here's the original, here's its inverse. We're going to check how that works with this, right? So into the inverse, I'm going to put the original. So again, here's the inverse, 7 over x plus 2. So here's the inverse, 7 over x plus 2. But the x has been replaced with the original function. So that original function has replaced the x right there. This x has been replaced by the entire function. All right. So now how do we simplify this? Well, anytime you have a fraction on the bottom here, fraction plus a number, you need to add two things like this. You need to have this thing turned into a fraction with the same denominator. Right now, this is like a 2 over 1. To make the denominator an x, we can multiply this 2 over 1. We don't see the 1, but we can multiply by x over x. So we end up with this. All right? So this has turned into this. Now we have a common denominator, so we can combine those two fractions on the bottom. When they combine into one fraction with the denominator of x. So these top parts across added over x. Now you see there's a negative 2x and 2x. Those will cancel. So you're going to end up with 7 over 7 over x. So this is actually 7 divided by 7 over x. So that's what we have, 7 divided by 7 over x. Just so we are clear, it's not 7 over 7 on top. It's 7 divided by 7 over x on the bottom. So there it is. And as you know, anytime you divide by a fraction, you can actually turn it into multiplication of the reciprocal. So that becomes x over 7. Those 7s will cancel, and we'll just have x. So it works. Definitely more complicated. The algebra here is tougher, but as long as you build some confidence with the algebra, you can get there. So this equals x. All right, let's try it the other way now. So now let's try putting the inverse into the original. So here's your original, and in that original, we're going to replace the x's with the inverse. So that x and this x will both be replaced with this inverse. So here it is written out, that function written out here. Both x's have been replaced by the inverse. Okay, so now how do we do this? I'm going to multiply -2 times 7 to get that on top, -14. Everything else is unchanged. Now I want to combine those two fractions. This is this fraction plus 7 over 1. We don't see the 1 over 1. So again, we want a common denominator. This says x plus 2, so we want the denominator of this, 7 over 1, we want it to be x plus 2 also. So we're going to multiply top and bottom for this 7 by x plus 2. So there it is. So that 7 has been multiplied by x plus 2 there and x plus 2 there. Now we have a common denominator, so we can combine the top. There it is written out when you combine it, -14 plus that. This has been multiplied, 7x plus 2 makes 7x plus 14. That's still over x plus 2 and x plus 2. Now you may know this rule, when you have a fraction divided by a fraction, but the denominators are both the same, you can just rewrite it straight like this. Basically, those are both of those are canceled. And the reason for that, again, is if you wrote this fraction, this divided by that, you can then do the reciprocal of this fraction, do multiplication, and the x plus 2 here will be on the bottom, this one will be on the top, and they will cancel each other. So there's that. -14 and 14 combines to cancel out to make 0, so we have 7x over 7, and the 7's cancel, we get x. So again, algebraically, it works out. This rule here leads to x. That means these are truly the inverses of one another. All right, here's from the practice assignment. This is why I made this video. I noticed this one in the practice assignment. I noticed it's a little bit tougher than the rest of the problems there. So here's this original function. We're going to find the inverse. First, writing it with y instead of f of x. Then turning it into the inverse by making this y and x and making both of these x's y. And now it is the inverse, but we want to solve the inverse for y. So I'm going to multiply both sides by y plus 3. So that y plus 3 is canceled, and now we have x and y plus 3 here. 2y plus 1 here. This we can multiply through. So we have xy and 3x. Now we get the y's on one side, so this 2y will be moved over here. And that 3x will be moved over there. Now I have y's here in both of these, so I'm going to factor out a y right here. And finally divide by x minus 2 on this side, so that we have y equals 1 minus 3x over x minus 2. That's our inverse. Now it has you in this question to try both of those, and if you do them both right, you will get x. Let's try the first one. You can try the second one on your own. So here I'm going to put the inverse into the original. So here's the original. I'm going to take this inverse, put it into here and here. So there it is. The original, both x's have been replaced by the inverse. This I'm going to multiply through. This one gets kind of crazy. Multiply that through there like that, the 2. Then I'm going to combine these. Again, this 1 has been turned into x minus 2 over x minus 2, which is the same as 1, but now we can combine those. Those combine, that becomes -5x. On the bottom, those can combine also. I made that 3 here, multiplied it by x minus 2 over x minus 2. Everything combines on the bottom as well. We end up with this. We have that x minus 2 that cancels on both. Leads to -5x over -5. And the -5's cancel, we get x. It works. Try this one. See if you can do some crazy algebra like that and make it work as well. It's a good challenge. And finally, another one for you to try. I'll leave you with this question. If you're given this function, find which function below is the inverse of it. So here are 3 different functions. One of these is the inverse of that. You could find it by taking this one and finding its inverse, and then you'll just find it's one of those. Or I would ask that you try doing the rule, like putting g of x, so putting that into there, or putting that one into there, or putting I of x into f of x. Put one of those in there, and if the result you get is x, then you have found which one is the inverse. So try putting this in here first, then this, and see if you ever get x as the answer, because then you'll know it's the inverse. All right, make sure you try everything in that practice assignment, and I hope you found these interesting, challenging, and informative. See you soon.